All right, so first we have a test on whatever the next day is. So exam 2 is Monday, 10/10, the day of my 13th wedding anniversary. But I'll be here with you. Yeah. So so you're taking the test in a fancy French restaurant. And the topics are first all the old stuff, and then vectors, and then 2D kinematics. And so the way to get ready for the test is the practice problems. You want to get to a point where you could explain why you made each decision along the way to the solution. And if you can do that, then you'll be good for the test. Anybody have any questions about the test? All right. And now so we're done with all the 2D kinematic stuff. I'd be happy, though, to answer as many questions as you want today about 2D kinematics problems. So if you want me to work through homework problems or whatever, just tell me which ones. When you're done with questions, we'll go on to the new stuff. But if it takes all hour, that's fine with me. So anybody have any practice problems that you'd like to see done or example problems you'd like me to explain? Yep.
I have two.
Okay.
Do you want to start with a vector question or 2D?
Vector.
Okay. So this is asking what are the components in the following coordinate system?
Mm-hmm.
And it's angle.
Okay.
It's an angle.
Do you have it with you? Can I just look at it? Which number?
It's C and D, so either of these. Probably both of them.
In number 1?
Yeah, the C and D.
From 1. That's fine. Okay. Okay, so number 1, there's a vector like this that makes an angle of 30 degrees with the horizontal. And it has a length of 50 meters. And it asks for the components in this coordinate system. And then in this coordinate system. And then in one that's rotated, where this angle is 30 degrees. And then another one that's rotated at a funny angle. So this time the y-axis makes an angle of 30 degrees with the horizontal. Okay, so for part A, there's the vector. The vector never changes. And we're going to use a coordinate system with the x-axis that way and the y-axis that way. So this is positive x, this is positive y, this is negative x, this is negative y. And so we have to figure out a counterclockwise angle from the positive x-axis to the vector. So this is the angle we want. So if you go, start at the positive x-axis, that's 90, 180, 270, plus 30. So the angle is positive 300. Negative 60 works the same. And so the vector that's v for vector, not velocity necessarily or anything. Oh, it's A. It's called in the problem. Okay, so the vector A is 50 times the cosine of 300 50 times the sine of 300 and that is to 25 negative 43.3. And if you use negative 60 for that, you'd get the same thing. Okay, so now part B. So there's the vector again. That doesn't change. And now the positive y-axis goes this way. The positive x-axis goes this way. And so the angle that we want is from the positive x-axis to the vector. That's 90 to get here, plus another 30, so 120. So the A vector is 50 times the cosine of 120, 50 times the sine of 120, and that is negative 25, positive 43.3. Any questions about those yet? Okay, so now C. So that vector is still the same. But now the coordinate system has the x-axis pointed also 30 degrees from the horizontal. So this is the positive x-axis. And this is the positive y-axis. That's the negative. So there's two ways to think about this one. The first is, so starting at the positive x-axis, what angle do you have to go counterclockwise until you line up with the vector? Zero. You don't have to go anywhere. You started there, you know. So this is 50 times cosine of 0, 50 times sine of 0. And you can just plug that in and you'll get 50, 0. But the other way you can think about it is, remember that finding vector components is the same thing as finding coordinates of the head once you put the tail at the origin. And so what are the coordinates of a point that's 50 meters along the positive x-axis? It's just positive 50, 0. And so that's the sort of simpler way to think about it. Any vector that's lying along the positive x-axis is just the length for x and then 0 for y. If it's lying along the positive y-axis, it would just be, like if we put the y-axis this way, it would just be 0, 50. if we had it lined up so the negative x-axis was lined up with the vector, it would be negative 50, 0. So you can just always think about calculating those vector components as being the same thing as calculating the coordinates of the vector's head. Okay? That's a nice way to think about it anytime the axis is lined up with the vector. Like, for example, brief digression. The acceleration in free fall is this, right? 9.81 meters per second squared down, okay? And we always use a coordinate system like this. And so the g vector is, you can think of this angle as 270 degrees or negative 90 degrees. And you get 9.81 times the cosine of 270, 9.81 times the sine of 270, and that gives 0, negative 9.81. Or you can also just notice that we're trying to calculate the coordinates of this point, which is 9.81 meters per second squared along the negative y-axis. And so it's just going to be 0, negative 9.81, and just don't mess with the angles. It does give the same thing, you know. So, all right, so the last one was D. Yeah. Yeah, so sine of 270 is negative 1. And so that just comes from the cosine and the sine. Thanks. She didn't believe me, but now she's like, I'm going to have to see that. Yeah, so the sines just totally come from the cosine and sine. Okay, so the last one has the y-axis pointing in this direction. So there's x, there's y, negative x, negative y. And so this one, what's the angle that you have to go from the positive x-axis to get to that vector? 90. And so it would be 50 times cosine and sine of 90. Or the easier way to think of it is the coordinates of the head are just 50 along the positive y-axis. So it's just going to be 0, 50. The same thing you would get from cosine and sine of 90. Mm-hmm. That, like in the problem itself, like that angle is meant to show that these are facing the same direction that this vector is. All of these three things are facing exactly 30 degrees from the horizontal. So we're just using that to know that for part C, the x-axis is lined up the same as the vector, and for part D, the y-axis is lined up the same as the vector. The dotted line is the horizontal.
Usually we take the angle for x and y, and so those broken lines show nothing in this case where we need to do it.
Well, if I didn't do that, you just wouldn't know. You'd know that these are both at angle, that these are all at angles, but you wouldn't know what those angles are. So that's just supposed to show that they're all lined up the same way. It shows that this and this and this are all parallel. That's what it's for. Any other questions about that one? Okay, and then you had a 2D kinematics question? Which one?
It was number 5, and you didn't have it as an answer for the displacement of part B.
Oh, okay.
So, and I'm just kind of curious.
Do you have those questions with you?
Yes.
Is that the basketball one? Should I go through this basketball one? It's sort of an unusual question. That's the wrong angle. Okay. So he is really tall. So we know that this distance is 15 feet. And anyone remember what that is in meters? 4.571 meters. So you should know that as a human on Earth, that 15 feet is the free throw distance. No, that'll be given. And then you should know that the height of the basket is 10 feet. That's 3.05, I think. Yeah, that guy's about 9'8". And so, let me be a little careful about this drawing. So what we really, this 15 feet, we're assuming is where it's shot from. So maybe he's standing a little behind the free throw line. And what we want to know is, what is the height the ball's shot from? And we're given that it's shot with a velocity vector of 7.8 meters per second. And that it is shot from an angle of 60 degrees. Okay, so 60 degrees above horizontal. So yeah, what height is the ball shot from, and then what's the displacement vector so what's the height h? And second, what's the displacement vector from the point where it's shot to the ball's highest point? Okay. So first, I'm just going to go through the whole thing because it's sort of an unusual problem. So first, we have to choose those four things. So an instant for time equals 0, an instant for time final, the origin location, and the coordinate system orientation. Time equals 0 is the instant it's shot. Time final is when it reaches the basket. And then for the coordinate system and the origin, I'm going to do what I do almost all the time. I'm going to put the origin on the ground beneath the object at time equals 0, and the y-axis up and the x-axis horizontal in the direction of motion. So the origin is on the ground. Beneath the ball at time equals 0. And the coordinate system has y up and x horizontal in the direction of motion. Any questions about those choices? And now figure out what we know and want. Do we know time final? No. Acceleration, it's in free fall, so we know AX is 0. AY is negative 9.81. Do we know P initial? We know the x component. If you're thinking of the coordinates of this point when time is equal to 0, the x component is 0. The y component we don't know, though. That's what we want to find. So we want PIY, but we know PIX is 0. Do we know anything about P final? We know them both. Yep. What we're trying to figure out is are the coordinates of the point where the basket is. So that's in the positive x direction 4.57, and in the positive y direction 3.05. Any questions about that one? That's doing something that these problems don't ask for that often. So PFX is 4.57, and PFY is 3.05. And then the initial velocity we can get from the speed and the angle. So for this one, we're going to use 7.8 times cosine and sine of 60. So our vector is 7.8. This angle is 60 degrees. Our coordinate system is this. So to get from the positive x-axis to the vector, it's positive 60 degrees. So 7.8 times cosine of 60, 7.8 times sine of 60. The x component is 3.9. What's the y component? 6.75. And then do we know anything about the the final velocities when it hits the basket? No. One thing that you might have noticed is that the x components of velocity never change in free fall problems. There's no x component to the acceleration, so the x velocity just stays the same the whole time. But we don't ever treat that as something we know. But if you ever saw a free fall problem where that didn't happen, that would be something you could use to notice that something must have gone wrong. Okay, so is there an equation that works with these? You don't have time final, and you don't have velocity final. So we're going to need to find TF first. So to find TF, we can use, I think we should be able to use PFY is equal to PIY plus VIY-TF plus 1/2 AY-TF squared. No?
No. It has to be x, because
We
we don't know PIY.
don't know PIY, right.
We're looking for
But we can do this with x in this one. You're right. Yes. And actually, remember where I said this problem is weird? That's what makes it sort of unusual. Like, in this kind of problem where you need to find TF, you almost always use the y equation and then plug it into the x equation. This one, you use the x equation and plug it into the y equation. It's the only example you're going to see like that, unless I put one on the test. Okay, so PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So 4.57 is equal to 0 plus 3.9 TF. AX is 0, so this term is 0. And so TF is just equal to 4.57 divided by 3.9. So what do you get for that? 1.17 seconds. And so now you can take this and add it to the list of things that you know. And now you can use PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So 3.05 is equal to PIY plus 6.75 times 1.17 minus 4.905 times 1.17 squared. So PIY is equal to 3.05 minus 6.75 times 1.17 plus 4.905 times 1.17 squared. And what do you get for that?
$1.876.
1.876 meters. And I did what you've always been taught to do, kept 3 significant figures through the whole problem, and then at the end expressed my answer in 4 significant figures. Any questions about that part? Okay, and then now we want part B, we need that displacement vector. So now we know the full PIY. To get that displacement, remember displacement is the position at the later instant minus the position at the earlier instant. The earlier instant is, this is PI. This one is the position at the highest point. And we don't know that yet, so we have to find that. So this we have. This is what we need. So we're going to have to choose a new time equals 0 instant, time final instant, origin, coordinate system. Well, some of this we can keep the same. Really, the only thing we're going to have to change is the instant for time final. Time equals 0, we can still make that the instant that it's shot. Time final is when it reaches the highest point. The origin and coordinate system, we can keep those the same. Since the origin and coordinate system are the same and time equals 0 is the same, all of the initial stuff that we had in the first part of the problem still hold. That's all they depend on is the origin, the coordinate system, and the time equals 0. But the time final stuff is all going to be different now. Okay, so do we know time final? No. No. We know acceleration. Do we know P initial? That's the same as before. So PIX is 0. PIY is, we just calculated that, 1 point, call it 88. VI is the same, so that's 3.9, 6.75. Do we know anything about V final? We do. So whenever you see highest point, you should think you're going to use the fact that the velocity, the y component of the velocity at that point is 0. So we don't know the x component of the velocity, but we know VFY is equal to 0. Well, we actually do know the x component of the velocity at that instant, but we're not going to use it. I'm going to pretend like we don't know it. But actually, this is what I just said. The x component of the velocity is going to stay 3.9 through the whole motion. And what we want to find is PFY. Well, we want to find PFX too. Okay, so is there an equation that'll let us solve for one of these? Yeah, we could use this one. 2AY times PFY minus PIY is equal to VFY squared minus VIY squared. Okay, we could use that one. That'll work fine. But then when we have to calculate the x component, it'll turn out we have to calculate TF anyways. So you don't have to see this to get through a problem like this, but I'm going to tell you that we need to find TF eventually. Let's just find TF first. That's not really a good place for a comma. Okay, let's calculate TF instead. I have my reasons. Okay, so to calculate TF, let's use VF. This has the benefit, too, of letting us use the really easy equation. So VFY is equal to VIY plus AYTF. So 0 is equal to 6.75 minus 9.81 TF. And so TF is 6.75 divided by 9.81. What do you get for that? Okay, so 0.69 seconds. And now we can plug that into the, so we can use that in the two PF equations. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 3.9 times 0.69 plus 0. And so what do you get for PFX? 2.69. And now we can do the same thing with the y component. So PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So PFY is equal to 1.88 plus 6.75 times 0.69 minus 1/2, I'll just write that as minus 4.905 times 0.69 squared. And what do you get for that? $4.20. Okay, so if you think of it as a vector, the PF vector is equal to 2.69. Does this match the solutions? I don't remember these numbers. Oh, okay. Oh, that's why I don't recognize these. Okay, so 2.69, 4.20. And so the displacement is 2.69, 4.20 minus 0, 1.88. So 2.69 and then 2.32. Any questions about that one? Are there any other questions, practice problems anyone would like to see? No more from Lillian.
Can you go back to the vector one?
Yeah.
Number 3?
Number 3?
Yeah.
Do you have that with you? Yeah. Oh, okay. So number 3, it says sketch the vectors 0, -2, +15, 0, 0, +9, and -5, 0. And this is the stuff I was saying about how to remember that you can always treat the vector components as the same thing as the coordinates of the head. So that's how we're going to think about this. Is what we're trying to do is plot the coordinates of the head, and then you can just draw the vector in. So for A, if the coordinate system is this, to sketch the vector 0, 2, plot the point 0, -2, sorry. Plot the point 0, -2. So that's, you don't go anywhere in x, you go down 2, and then just draw the vector into place like that. So that vector is this. I don't really know how you draw, well. Okay, so for part B, we're doing +15, 0. So plot the point +15, 0. That's out here. And then the vector goes from the origin to the point. So the vector is this.
If something like this would be on the exam, do you want us to label like 15 or anything like that?
Yes, that would be nice. I think probably I would give full credit for just drawing the directions, though. And then the next one is 0, +9. So plot the point 0, 9. And then the head's there, and the tail is at the origin. And then the last one, -5, 0. So that was weird. Okay. So plot the point -5, 0. That's out here. Go from the origin to that point, and then that's the vector. Any questions about that one? So anytime you have, anytime one of the coordinates is 0, these vectors are pretty easy to sketch. And likewise, anytime you have a vector that lies along one of the coordinate axes, coming up with the components is sort of automatic. You can just sort of eyeball it, say it's in the negative y direction, positive x direction, that kind of thing. Any other questions, problems you'd like to see? Yep.
Number 3. I once had a problem like making a great equation because we started doing one equation. Is there ever run into it where we can do one equation or we'll use 2 equations, but we'll use one, and then the second one we get the same answer?
Yes.
So
Yeah, I think there's always more than one way
okay.
to get to any answer. There's like a fastest way, but that doesn't really matter too much. You can, if you do it right, you can always work around another way and get the same answer.
Because I was doing the first one and I was like trying to make sure I was doing it, and I was like, well, crap, this is one
Yeah.
equation, and then I went through and
Right.
like, oh, well, I should have kept doing that.
Yes. Yep, that works fine. So you want to go through it?
Sure, yeah.
So this is 2D kinematics. Number 3. And it says a ball is thrown from a height of 1.8 meters, initial speed of 28 meters per second at 25 degrees above horizontal. So it looks like this. That initial speed is 28 meters per second. And this angle is 25 degrees. And this height is 1.8 meters. And the first thing we want is how high is it at the highest point? Then we want how far has it traveled horizontally when it gets to its highest point? And then the third one is how far has it traveled horizontally when it hits the ground. Okay, so for part A, time equals 0, time final, origin, and coordinate system. Time equals 0 is when it's thrown. Time final is when it reaches the highest point. And then I'll use the coordinate system on the ground beneath the ball's position at time equals 0 and oriented like that. So the origin is on the ground beneath the ball at time equals 0. And the y-axis is up, x-axis is horizontal, in the direction of motion. We don't know time final. We know the acceleration. The initial position is 0x 1.8y. PF, we're trying to find PFY. VIX and VIY we can get because we know the vector has a magnitude of 28. Makes an angle of 25 degrees with the horizontal. So this will just be 28 times cosine of 25, 28 times the sine of 25. I just saw this earlier, but I can't remember what this is, 25 point something. I wish I would have remembered, because then I could have pretended like I did that in my head. You would have thought I was smarter. And we don't know anything. Oh, that's not true. We do know something about the final velocity. Highest point, so that means we're going to use the fact that the y component of velocity is 0. So VFY is equal to 0. Okay, so we can use this equation. I think 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So 2 times negative 9.81, that's negative 19.62, times the quantity PFY minus 1.8 is equal to 0 minus 11.83 squared. So you can divide both sides by negative 19.62, and you get PFY is equal to 1.8 plus 11.83 squared divided by 19.62. What do you get for that? 8.93 meters. And then for part B, well, we're looking for the x component of the position when it reaches the highest point. So we can keep all those choices we have to make the same, which means we still know all the stuff that we knew before. So we still know all this. And we also know PFY is 8.93. And we're trying to find PFX. I think there's nothing that works, so we have to find time final. So we can do that with VFY is equal to VIY plus AYTF. So 0 is equal to 11.83 minus 9.81 TF. So TF is 11.83 divided by 9.81. What's that? 1.20? 1?
1.20. 1, yeah.
Okay. 29?
No, 1.21.
Okay. And so now that's one more thing we know. And now we can go to this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 25.38, is that what it was? Times 1.21. The x component of acceleration is 0, so this is all we have. And what's 1.21 times 25.38? Any questions about that one? And then the last one, we're trying to figure out how far away horizontally it hits the ground. So our choices are time equals 0 and time final instant. We have to revisit that. Our time final before was when it got to the highest point, so that can't tell us anything about when it hits the ground. So we can keep our time equals 0 instant the same, but our time final needs to be when it hits the ground. These two things can stay the same. I think I'm not going to go through this whole thing, but let's think about what we know and what. Do we know time final? No. Do we know acceleration? Yes, it's free fall. The initial position is the same as it was before because we didn't change our time equals 0 or anything about our coordinate system. So that's 0, and PIY is positive 1.8. P final, do we know anything about that? Yeah, we know PFY is equal to 0. That's how we're going to specify that we're looking for when it hits the ground. And we're trying to find, oh yeah, this won't be so hard. Maybe we'll solve this. All we're looking for is PFX. VIX and VIY are the same as they were in the first part. So that's 25.38 and 11.83. And then VF we don't know anything about. Is there any equation that works with this? No. So we need to find time final. So we can use this equation. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 1.8 plus 25.38 TF minus 4.905 TF squared. Okay, so how do we solve this equation for TF? Quadratic formula. Can someone who has that in the calculator punch that in for me? Oh, I got VIX there. Thank you. That should be the other one. Thank you. 11.83. Seconds. And the other one is negative. Negative point? Yeah. So we know it's not that one, so we know it's this one. And now we can plug that into the x equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 25.38 times 2.56. AX is 0, so that term goes away. And what do you get for PFX? I'm not changing it. Any questions about that one? Any others? Yep.
Are we able to do just number 2, part D?
Yes, that's a good question. Okay, so number 2 is the one with the helicopter. And as you know, I like drawing helicopters. Okay, so, this one, I could have made it a little more clear. I could have made the wording a little better. If I would have said that the helicopter is moving with a constant velocity at a speed of 20 meters per second. So, what I didn't emphasize is that the helicopter is just continuing along this path. The way that I did it, that was my thinking. The helicopter is just doing this. It's not speeding up or slowing down. It's not turning. It's just continuing like that. And so if you didn't get that from the wording, then you couldn't really do this part of the problem. But if you recognize that the helicopter is moving with a constant velocity, and you remember that constant velocity is the same thing as zero acceleration, so constant velocity is exactly the same as zero acceleration. Because acceleration measures how quickly velocity is changing. If velocity isn't changing at all, acceleration is 0. You can just think of those as synonyms or whatever. So parts A, B, and C ask you stuff about like where the object hits the ground, the highest point. D asks how much higher is the helicopter when the object hits the ground. So one thing we would have already known is how part B asks how long it takes for the object to hit the ground. Anybody have that time? Okay, so B gave us time final equals 3.918. Okay, so now we'll make those 4 choices. Time equals 0 is when the object is released. TF is when the object hits the ground. The origin, let's say, is on the ground beneath the release point. And the coordinate system has the y-axis up and the x-axis horizontal in the direction of motion. Okay, so let's think about what we know and want. Do we know time final? Yep, TF is 3.918. Do we know acceleration? This is the key to this part of the problem. Yeah, so it's a constant velocity. The helicopter is not in free fall. Even though there's nothing touching it, the air is touching it, and helicopters are designed specifically to create a lot of air resistance. You know, they fly by creating force from a lifting force from the air. So it would have to be a really bad helicopter to be in free fall. That's a really undesirable quantity in a helicopter. So AX is 0, AY is 0. And then the initial position, PIX is 0. PIY, I think it was 55 meters, it says, above the ground. The initial velocity of the helicopter is, so it's 20 meters per second at 15 degrees. Does anyone have what those components are?
For PIY, 5.176.
That's why.
Yeah. And then VIX is 19.318.
And then we don't know anything about the final velocity. But what we're trying to figure out is PFY. We want to figure out how much higher it's gone over this time interval. So I think we can use the equation that says PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So PFY is equal to 55 plus 5.72 times 3.918. And then the y component of the acceleration is 0, so that term's 0. And what do you get for this?
77.4.
77.4 meters. Okay, so is that the answer? That's the bulk of this question, but it asks how much higher the thing is than when it was released, you know, how much higher it's gotten in that time. And at the start of this interval, its height was 55. So it got 77.4 minus 55, which is 22.4 meters higher.
So basically that's the displacement from...
Yeah, that's the y component of the displacement. That's a good way to think about it.
So on the thing, I got you had 20.280. I was saying, oh, is that what that number? So I was looking at the solutions and I got totally stumped on that one because.
And you got something more like this?
Well, I think you might have put the displacement on there instead, 20.280 meters for part B.
Uh-huh.
On the solution, that's what you had. So I think.
But you got a number like this when you did it?
No,
Oh, you didn't do that part.
Yeah, I got lost, so that's why
I don't know.
Yeah, because you actually did 0 plus 5.1.
Oh, okay. So the way that I did it in the solution is instead of choosing my my origin location to be on the ground, I chose my origin location to be at the helicopter at the instant it's dropped. And so then when my PFY actually was how much higher it went. I didn't have to subtract the initial because the initial was 0, you know. But I don't have an explanation for why we just got 22 and on there I got 21.
Yeah.
It's a little too big for round off error, but I don't know. Okay, that's all.
That's right there.
Well, I don't know. I don't know if it is. What do you want from me?